Welcome to your lecture from 2.6. I have previously recorded this 2 times already. Here's hoping that the 3rd time is the charm. Right? Right. Section 2.6. In 2.2, we looked at things called vertical asymptotes. And in section 2.6, we're going to look at horizontal asymptotes. For example, let's consider this rational function. This rational function right here has in the denominator a function that can be factored. And if you notice by looking at the graph, you see a vertical asymptote here and another vertical asymptote here. And so we can see that, yes, there are definitely some asymptotes. Specifically, if we look at 2, the value of 2, draw the little asymptote in there, we can see that for x equals 2, as f of x is approaching 2 from the left, over here, that f of x is approaching negative infinity. And as f of x is approaching 2 from the right, over here, we can see that f of x is approaching positive infinity. So therefore, we've got a vertical asymptote at x equal 2. We also have another vertical asymptote here at negative 3. We talked about that earlier. And that also has similar behavior. One side goes to infinity, the other side goes to negative infinity. But are there any other asymptotes? Yeah, there actually is, a horizontal one. So a horizontal line, y equals L, is called a horizontal asymptote of the graph of the function y equals f of x if either f of x approaches L as x goes to infinity, or as f of x approaches L when x goes to negative infinity. For the horizontal asymptote, we investigate how the function f of x behaves as x approaches negative infinity or positive infinity. This is also called end behavior. Let's take a look at these functions. For this example, I've got a graph of f of x. Now notice, graphs do not cross their vertical asymptotes. Why? Well, that's typically where they have holes or discontinuities in their domain. But a graph may or may not cross the horizontal asymptote. So for example, let's look at this first function here. This first function here, we see we've got a horizontal asymptote at about 2.5. That's in purple. If you notice here, look at my graph crosses the horizontal asymptote here. And then the graph also crosses the horizontal asymptote here. Now notice, as x is going to negative infinity, the function is coming up towards that horizontal asymptote from the bottom. And as x approaches positive infinity, f of x is approaching that horizontal asymptote from the top. Let's look at our next function, sine of x over x. We looked at this one earlier, but I didn't have a cool graph like this. So for sine of x over x, the last time we looked at this was when x was approaching 0. As we know that there's actually a hole there, you just can't see it in this graph. But did you know for the end behavior what happens? Yeah, look at that thing. It just kind of oscillates over and over and over again, but it's getting smaller and smaller and smaller with each oscillation. In this case, as x is approaching positive infinity, this function is approaching 0. And as x is approaching negative infinity, this function is also approaching 0. These are two examples of functions with horizontal asymptotes. The first one has a horizontal asymptote at 2.5. And the second one has a horizontal asymptote at 0 for both sides. Some graphs may have more than one horizontal asymptote. For example, this function, if you were to graph it, we actually see two of them. We've got one horizontal asymptote at positive 2 and one horizontal asymptote at negative 2. So let's figure out how can we find those horizontal asymptotes. If r is greater than or equal to 0 is a rational number such that x to the power of r is defined for all values of x, then we can say that 1 over x to the r of that function as x approaches positive or negative infinity will always equal 0. In other words, if I have if I have 1 over x to the third, as long as I make x approach infinity or negative infinity, this will always give me 0. And think about that. Doesn't that kind of make sense? Let's say I have one cake and I divide it amongst infinitely many people. Well, the slices are going to be so small, everyone's going to feel like they didn't get any cake at all. Yeah. This is true for negative infinity and positive infinity. And for powers of r, that will give me rational positive numbers. So note, most of the limit laws that we learned in section 2.3 are valid if we replace x approaches a with x approaches negative infinity or positive infinity. That's just most of them though. You'll see as we do some examples. So let's look at the ones that I graphed earlier. But besides using a graph, let's find out how we are going to find the limit of this function. Here's a hint. Always take a peek at the degree of your denominator. That degree, that's what you're going to use for r in your 1 over x to the r. So for this function, the degree of my denominator is 3. So what I'm going to do is I'm going to multiply the top of my function by 1 over x to the 3, and then I'm going to multiply the bottom of my function by 1 over x to the 3. Because if I were to plug infinity in right now, I just get a mess. So let's take the top and multiply it by that 1 over x to the third power. And I'm going to do the same thing to the denominator. Now what I'm going to do is cancel the powers of x. So for my first one, here I've got 5x cubed over x cubed. That's going to simplify into 5. Next, I'm going to simplify this one. 4x over x cubed is going to give me 4 over x squared. And then I'm going to simplify the denominator next. So I'm going to end up with 2. Oops. Sorry, there's a little thing I keep pushing on my pen and I don't know how to not push it. Namaste. Namaste. The irritated in me acknowledges the irritated in you. Ugh. Technology, you're pissing me off. Okay. So after I've simplified it, I've got this neat little thing. Well, notice what happens. If I plug in infinity now for these pieces, this would be like saying 4 over infinity. And we know from that definition earlier that that's going to be equal to 0. Like if I have 4 cakes and I divide them amongst infinitely many people, everyone's still going to be disappointed. So that's going to equal 0. Same with this, 1 over x, that's going to approach 0. And then same with this, 3 over x squared, that's going to approach 0. And for this limit, what I end up with is when I plug in the infinity, 5 plus 0 all over 2 minus 0 plus 0, which gives me 5 halves. And that happens to be my horizontal asymptote. And we can find that using the limit as x approaches infinity. Cool, huh? All right, let's look at the next one. The next one, I've got, again, the denominator, although this one's a little bit trickier. So look at the degree of your denominator. And in this case, the degree of my denominator is 1. So that means r is going to equal 1, or I'm going to use 1 over x for the numerator and the positive, or for the numerator and the denominator. I'm going to use 1 over x for the numerator and the denominator. All right, so we do also have this other thing coming up. Keep in mind that if x is less than 0, then when I take the square root of x squared, I'm going to get a negative x. How do I know that x is less than 0 for this problem? Well, I'm approaching negative infinity. Since I'm approaching the limit of negative infinity, if I have to take the square root of anything, I am actually not going to use the plus or minus, but I am going to use the negative because they said it was negative. All right, let's actually do this problem. So first things first, I'm going to multiply the top by 1 over x and the denominator by 1 over x. And then I'm going to do the limits. All right, so the limit as x approaches negative infinity of 4x squared plus 9 divided by x in the top. And then in the denominator, I'm going to get x over x and 1 over x. Now, how do I get this x here to play with the square root on top? Well, If I want to put something inside a square root that's already outside the square root, I just double its power. So an x squared outside the square root is an x, so an x outside of a square root is an x squared inside the square root. Let me write that down. I'm going to do some simplifying first. So an x squared outside of a square root, damn it. So an x outside of a square root is an x squared inside the square root. I'm not going to worry about that negative yet because I haven't plugged in the negative infinity. All right, as you were. So I've got the limit as x approaches negative infinity. I'm going to simplify. Here I've got 4 plus 9 over x squared. And then in the square root. And in the denominator, I've got 1 plus 1 over x. Excellent. Now I've got everything simplified. I can plug in the negative infinity. So when I plug this in, whether I divide a piece of cake into infinitely many pieces or negative infinitely many pieces, remember that 1 over x to some power is going to turn into 0. So what I end up with in the numerator is the square root of 4 plus 0. And in the denominator, I end up with 1. Okay, square root of 4 is plus or minus 2, correct? So square root of 4 is plus or minus 2, but remember, we are dealing with the limit as x is approaching negative infinity. So that means that we're going to choose the negative 2. So my horizontal asymptote is going to be y equals negative 2. Now this one's interesting because it doesn't have a denominator, at least not yet. If I plug in the limit as x approaches infinity, what I'm going to get here is infinity minus, here I've got infinity squared plus 2 times infinity. As I evaluate this, I'm going to leave this front infinity here. Infinity squared is just infinity. 2 times infinity is also infinity. And infinity plus infinity, that's going to give me infinity. And then the square root of infinity also gives me infinity, and blah, blah, blah. I finally get to this when I plug it in. I get infinity minus infinity. We can't say what infinity minus infinity is. So we have to do some math, smoke, and mirrors. Why does it keep switching? All right, so infinity minus infinity is a conundrum. So we got to do some math, smoke, and mirrors, or as we also call it, math magic. So let's do it. The math magic I'm going to do here is I'm going to multiply by the conjugate. So I've got the limit as x approaches infinity of x minus the square root of x squared plus 2x. And I am going to multiply that by the conjugate. So I'm going to turn this into a fraction. And I'm going to multiply it by x plus the square root of x squared plus 2x. And I'm going to multiply the top of the fraction and the bottom of the fraction by the same values. When I multiply, the denominator is super easy. I'm just multiplying that by 1. So the denominator is just going to be this pesky little guy. The numerator, on the other hand, this is actually a difference of squares. If you don't believe me, that's okay. You can multiply it out the long way. And you'll notice that the middle terms cancel, and that when I square the first and the last, I end up with x squared for the first one, and then the last one makes the square root disappear. But don't forget that it's a difference of squares. Okay, if I distribute this negative sign, what happens is that my x squareds are going to cancel. And this negative sign, when I distribute it to the 2x, I'm going to end up with the limit as x approaches infinity of negative 2x all over x plus the square root of x squared plus 2x. All right, now I have a denominator, right? Now I have a denominator. So if I look at the degree of the denominator, I have it's x to the 1. I know I have an x squared in the denominator, but that's inside a square root. So that also has an effective degree of 1. So I'm going to multiply the top and the bottom of this fraction by 1 over x. So when I multiply it out, I'm going to end up with negative 2 on the top. On the bottom, I'm going to end up with x over x. Oops, I'm writing over my controls here. Plus, now remember when I put it inside the square root, the power is going to double. So when I multiply the 1 over x by the square root, I'm going to put it inside with an x squared. And this is going to give me negative 2, when I simplify, over 1 plus the square root of 1 plus 2 over x. All right, this is where we want to be, right? This is where we want to be. Because now I can plug in my x equals infinity, and this bad boy turns into 0. And what I end up with getting is negative 2 divided by 1 plus the square root of 1 plus 0, which gives me negative 2 over 2, which is going to give me negative 1. Cool, huh? So this thing has a horizontal asymptote at y equals negative 1, because the limit as x approaches infinity of this thing is going to give me negative 1. Remember, you can graph this function and plug in values that are way, way, way big, like 10, 100, 1,000, 10,000, 100,000, yada, yada, and verify that it's correct. Okay, for this function here, it's actually going to be very helpful for us to look at what's happening on the inside. Let's look at the inverse tangent function. The inverse tangent function actually has horizontal asymptotes at pi over 2 and negative pi over 2. And this is for plain Jane inverse tangent function. We'll just say like the inverse tangent function of theta. Okay. We don't have plain Jane inverse tangent function. We have the inverse tangent function of 1 over x minus 2. And we'll deal with that in a second. All right, so this is what the inverse tangent function looks like. So basically, as theta approaches positive infinity, okay, as we go out here to the end behavior, we can see that inverse tangent is approaching pi over 2. And as theta is approaching negative infinity, so out in this direction, we can see that the inverse tangent is approaching negative pi over 2. So what we need to figure out is what's happening with the inside. Specifically, let's look at the theta being equal to 1 over x minus 2. And then let's look at the graph of 1 over x minus 2. So 1 over x minus 2 has a vertical asymptote at 2. And with the vertical asymptote at 2, we can see that on the left side of the vertical asymptote, that the function is approaching negative infinity. And on the right side of the vertical asymptote, the function is approaching positive infinity. So if x is approaching 2 from the positive, that means that we're using the right side. So this limit, as x approaches 2 from the right, of the inverse tangent of 1 over x minus 2 is like saying the tangent, the inverse tangent, as the inside approaches positive infinity. Well, we can see from our graph that if theta is approaching positive infinity, that the inverse tangent function is approaching this horizontal asymptote of pi over 2. So this thing is going to be pi over 2. Similarly, in the next screen, if we have, as x is approaching 2 to the left, using the graphs and information that we had previously, this is like saying the inverse tangent of negative infinity. And again, if we look at the graph of the inverse tangent, for negative infinity, this thing is approaching the horizontal asymptote of negative pi over 2. So this one's going to be equal to negative pi over 2. Now these inverse functions are the one where you don't have so much manipulation that we're going to use mathematically, but we still need to know how to do the other ones using math magic. So keep that in mind. Little combination moves here of graphs and math to make the world go round when you are finding limits at infinity.